Welcome to Mrs. Neller's notes for her pre-calculus class. These are the notes for section 3.7, day 1, entitled Rational Functions. And today we're just going to focus mostly on the first objective, which is to explore rational functions and talk about what their asymptotes are. A rational function is basically a function where the numerator and the denominator are both going to be polynomials, and they have no factor in common. Now sometimes you can factor them and you can cancel some stuff out, but we're not going to see many of those. Okay, but we still might have to factor even though they don't have a factor in common. And these graphs have a very different behavior from the graphs that we've seen in the past. So the polynomial functions we've seen up until now have lots of curves in them, and these still have curves, but they have something extra and unique about them. Okay. And as we're going through these graphs, we're going to find all different kinds of information about them. We're going to find domain, and we're going to find range. We're also going to find our x-intercepts and our y-intercepts. And we're going to talk about two new features as well, called the horizontal asymptote and the vertical asymptote. Okay, so the domain, again, is just whatever values make the denominator 0. Okay, and the range is going to be any restrictions that we have in the y values. And that'll be a little bit clearer once we start to talk about our horizontal and our vertical asymptotes, because there is a connection between them. So let's just start with a really simple function, a really simple rational function, just so we can see what these actually look like. And you can type this into your graphing calculator, go to y equals and type in 1 divided by x. And when we're making our table of values, we have x and we have f of x, we're going to need a lot of values here. I'm going to start at -4. And let's go to +4. And at -4, we get a decimal. And then we get another decimal for -3. And at -2, we get a little bit bigger. At -1, we get -1. But at 0, our function is undefined. You can't divide 1 by 0. And that's important. That's a special feature of the graph that we'll talk about in a moment. For 1, we get 1. For 0.2, we get 1/2. For 3, we get 1/3 or 0.33. For 4, we get 0.25. And we could continue on. We could do even more values if we wanted to. Okay, I'm drawing my axes here. And then we'll start to plot some of these points. And at -4, -1/4, it's really close to the axis. -3 is just a little bit more. Might be kind of hard to graph. -2, 0.5, -1/1. Okay, so even though we have some really small values here, we can see that the graph goes like this. So at 0, it's undefined, and then when we get to the positives again, we have 1/1, and 2.5, and 3 1/3, and 4 1/4. So again, the graph's going like this. Now, you might ask, how do you know that it's getting really, really close and going up? How do you know it's not actually connecting here? Now, if you graph on your graphing calculator, you'll see this type of a graph. However, your graph is going to connect the really low point to the really high point. So you have this line that gets connected down the middle of your graph. So you'll have your two swoops, as I like to call them, and then you'll have a line that connects them. And actually the calculator is wrong when it puts that line in there. That line's not supposed to be there. Now, these lines are our x and y axis, but they're also going to be lines that the graph never touches. So as x is going to negative infinity, our y values are getting closer and closer to 0, but they never actually touch it. And as x goes to 0 from the left, it starts to go to negative infinity. And then as x starts to go from towards 0 from the right, it goes to positive infinity. And as x starts to go to positive infinity, our y values go to 0. Okay? So basically, this is going to be our horizontal asymptote because it never touches it. It's a horizontal line that the graph never touches. And this line here is going to be our vertical asymptote because, again, it's a vertical line that our graph touches but never crosses. I mean, it approaches, but it never crosses. So here's the book version of their table and their graph, a little bit neater than the one I drew. And they have this notation in there as well about how the behavior of the graph can be notated. And there's something new in these notations. There's this little 0 with a little plus by it, and then you have a little 0 with a negative. That means as x approaches 0 from the left, that little negative there means that we're coming from the left side. So you're coming towards 0 as you're moving from negative infinity and up towards 0. And here, this means that you're coming towards 0 from the right. So you're starting over here by positive infinity and you're coming towards 0. Okay? You're going to see that notation a lot. And sometimes it's good to write that notation, and sometimes it's better just to test some points to see where your graph is going to be actually plotted out. And we'll talk more about that in a moment when we get to some more complicated graphs. But going back to our domain and our range of this function, our domain, remember, is all the values that we can substitute in for x except anything that makes the denominator 0. So my domain is going to be all of the x's except for x equals 0. Can't have 0 in there. And remember that our graph didn't touch the y-axis either. Okay, it didn't touch the x-axis and it didn't touch the y-axis. Okay, so remember x equals 0, that's actually the y-axis. And y equals 0 is actually our x-axis. So since our graph didn't touch y equals 0, that's our limit on our range. We had every y value covered except for y equaling 0. Now, as we got closer and closer and closer to those asymptotes, we had some special behavior for the graph. So if you take a look at these values, or if you substitute them into the equation, it might be easier just to substitute them in than to change the values on your calculator. But if you do 1 divided by -1, we're going to get a -1 out. 1 divided by -1/2 is -2. 1 divided by -0.1 is -10. And then we get -100 and then -1000. So just for those values here, this is as the graph is approaching 0 from the left. So that's as the graph is approaching 0 from the left. So I'm getting closer and closer and closer to 0, but I'm never actually getting to 0. So as x approaches 0 from the left, we can definitely see that y is going towards negative infinity. So all of a sudden we're going from -1 to -2 and then to -1000. So if I keep getting even closer to 0, if I did -0.0001, I would get, -10,000. So we're going to keep getting closer and closer towards that negative infinity, but we're never going to get to 0. Okay, now remember at 0, the graph doesn't exist. That was like what we had in our table here. Okay. But now if I start to put in some positive values that are really close to 0, but not actually 0, let's see what happens. And I'm going to start down here actually with 1. 1 divided by 1 is 1. 1 divided by a half is 2. 1 divided by a tenth is 10. And then you get 100. And then you get 1,000. So as x gets closer and closer to 0 from the right, our y values are going to go towards positive infinity. So that's kind of a table way to prove that the shapes of these graphs are accurate. That as I get into these values here, these really small negative values or these really small positive values, the graph is going to get closer and closer and closer to 0, but never actually get to 0. So that just verifies the behavior of our asymptotes. So, like I said, in that graph, the line x equals 0 is going to be called our vertical asymptote, and the line y equals 0 is our horizontal asymptote, because that was the parts of the graph, or the parts of the graph grid that our actual graph never touched. It got close to it, but it never actually touched it. And I know I keep saying that the graph is going to get closer and closer to the asymptote, but never actually touch it. Sometimes the graph does actually cross the asymptote. Okay? So here the graph, or the book does a really good job with these graphs of showing how here's a couple vertical asymptotes and how the graph is approaching it but never touching it from either direction. Okay? Same thing here. And again, here's a horizontal asymptote, so the graph is going to approach it but never actually touch it. But this graph here shows the horizontal asymptote, and then the graph is close to it, and then it actually crosses it. Okay? And that seems a little contrary to what I've been saying, but we have to remember that the asymptote behavior that we're drawing in our graph is going to represent the behavior of the graph at either positive or negative infinity. So even though we might zoom in on a small part of the graph where the graph actually crosses the asymptote, the end behavior is going to be described out here where it's going towards negative infinity. Okay, so just keep that in mind that sometimes you might have a graph that's going to cross the asymptote. It is a dashed line, it's not a solid line, so there are openings where the graph could get through. Now this slide is really, really important. This information here is a basic summary of all the information that you're going to need to look for and how to do it so that you can graph these graphs. Okay? The vertical asymptote is always going to be some equation. It's going to be x equals some number. That's the equation for any type of a vertical line. And it's going to occur at the value that makes the denominator 0. So if your denominator is x minus 5, then the value that your denominator couldn't have would be 5. So then x equals 5 would be your vertical asymptote. That would be where the graph doesn't exist for that value. And it's the same thing for the horizontal asymptote. It's going to be an equation that is y equals some number. But there's a couple different ways that we get this. Okay, it's not so much what the denominator can't be. We have to look at the numerator, okay, and we have to look specifically at the degree of the numerator. So if the degree of the numerator is equal to the degree of the denominator, so that means you have x squared over x squared. Then to find your equation for y, you write the ratio of the lead coefficients. So you might write y equals 3 over 4. If the degree of the numerator is less than the degree of the denominator, then your horizontal asymptote is always going to be y equals 0. So if the degree of the numerator is less than the degree of the denominator, that's like when you have x over x squared. And then the degree of the numerator might also be greater than the degree of the denominator. And if that happens, then there's no horizontal asymptote whatsoever. Absolutely none. Because if that happens, then you would have like x squared over x, and you would be able to cancel and reduce that down so you got rid of the denominator, and then you just have a linear function. Okay? So keep those characteristics in mind. Maybe write them at the top of your homework or refer to them in your notes as you're going through your homework. And we have a couple more examples to do, and then we will be done for today. And we're just going to take a look at some more complicated rational functions. Okay? And we're not going to focus a whole lot on the transformations, but all those transformation properties that we've talked about, like adding or subtracting, can move a graph up or down. Multiplying can stretch a graph. Adding or subtracting inside the parentheses with x can move the graph left or right. All those transformation properties are still going to apply. But as we go through these functions and we graph them, it's a little bit more systematic, I think, to go through and write down your x and y intercepts, your horizontal and vertical asymptotes, and then your domain and your range. Once you draw in your horizontal and your vertical asymptotes, then you can test some points to see where the little swoopy parts of your graph are going to be graphed. Okay? So, for this function, we have 2 over x minus 3. Now, I like to start off by finding the x and y intercepts first. The y-intercept, you just plug in 0 for x. So if we plugged in 0 for x, we would have 2 over negative 3. So our y-intercept is going to be 2 over negative 3, or negative 2/3. The x-intercept, the trick with the x-intercept is that it's basically whatever makes the numerator equal to 0. And here, I don't have to worry about that. So we actually end up having no x-intercept, because I don't have a variable here in my numerator. I just have a number. I have 2. Okay? So if I had some sort of variable in there, then I would have something to set equal to 0 and solve for that variable. But in this case, I don't. Okay, now I need to focus on that new piece with my horizontal asymptote and my vertical asymptote. Okay, now remember the horizontal asymptote, we have to look for the degree of the numerator and the degree of the denominator. Now the degree of the numerator here is 0, because I would have 2x to the 0. My degree of my denominator is 1. So the degree of the numerator is less than the degree of the denominator, so that means it's automatically y equals 0. And then my vertical asymptote is whatever makes the denominator equal 0. So if I took x minus 3 and set it equal to 0, I would get x equals positive 3. Okay? So again, to find the y-intercept, you plug 0 in for x. To find the x-intercept, it's whatever makes the numerator equal to 0. The horizontal asymptote, you're comparing the degrees of the numerator and the denominator. And then for the vertical asymptote, it is whatever makes the denominator 0. So now, if I were to graph this, let me put in my axes. And after you have that, the very first thing I like to graph, even before I make my table of values, is the horizontal asymptote and the vertical asymptote. So my horizontal asymptote was y equals 0. So that's actually my axis. So I could even switch colors here to show where those are. Okay. So there's my horizontal asymptote. I'm going to put a dashed line. And my vertical asymptote is at 3. So again, I'm going to put in a dashed line. Okay. And now I need to test some values. And that means I need to test some values that are to the left of 3 and to the right of 3 and see if I get positive values or negative values. If I get positive values, I'm going to be above y equals 0. If I get negative values, I'll be below y equals 0. Okay? And you can do this on your calculator. You could type in y equals 2 divided by x minus 3, but make sure you put the x minus 3 in parentheses in your calculator. Okay? And when you do that, I also know that my y-intercept is going to be 0 and then negative 2/3. So that's going to be right about here. So that tells me I get a negative value here. But if I plug in 2, 2 minus 3 would be negative 1. So that's going to be a negative value. Okay, 2 divided by negative 1 would be a negative value. If I put in a 1, 1 minus 3 is negative 2, so 2 divided by negative 2 is a negative value. So again, I'm going to be down here. If I plugged in 0, I get my y-intercept. Even if I plug in negative 1, I still get 2 over negative 4. That's a negative half. Okay, so I know that this part of the graph is going to be down here in these negative regions. Okay, and now the nice part about most of these very simple functions is that they're kind of opposites. So if I have one graph down here in the third quadrant, my other graph is most likely going to be up in the first quadrant. But still, let's test a couple points here. Let's say I don't want to test 3, but I can test 4. If I put a 4 in there, that would get me 2. So that's going to be up here. If I put in 5, 5 minus 3 is 2. So 2 over 2 is 1. So it's still going to be over here. Okay? So I know that my graph is going to be up in this region. And that's good enough for now. I'm not going to get real hung up on you plotting specific points. If you want to put some specific points in there, you can. Definitely put your y-intercept and your x-intercept. Notice that we don't have any x-intercept because we're not crossing that x-axis anywhere. Okay? Now the other two pieces of information we need are our domain and our range. And for my domain, that was the x values that I could not have. I couldn't have x equals 3. Okay, notice that that's the same as my vertical asymptote. That's supposed to happen. And for my range, the only y value that this graph doesn't have is at 0. So that's going to be all the y's such that y cannot be 0. And yeah, there's a connection between your horizontal asymptote and your range. Okay? So for right now when you're graphing these, you don't have to rely too much on your graphing calculator. You can just test a few points and just kind of estimate where those little swoops of the graph will be. Okay, so let's go through one more and then we'll be done. This rational function is a little bit more complicated. I have 3x plus 5 over x plus 2. So my numerator is a lot more complicated than the previous one. I'm still going to start by finding my x and y intercepts. For my y-intercept, I would plug 0 in for x. So that would get me 5 over 2. And then for my x-intercept, remember it's the value that makes the numerator equal to 0. So if I take the 3x plus 5 and set it equal to 0, I have to subtract the 5 over and then divide by 3 to solve for x. So I would get negative 5/3. And that's kind of irritating. That's a fraction, but that's okay. We can handle that. For my horizontal asymptote, remember I have to look at the degrees. So now the degree of the numerator and the denominator, they're the same. I have x to the first and x to the first. So when that happens, I want to make a ratio of my lead coefficients. So I'm going to have 3 over 1. So that'll be y equals 3. And then for my vertical asymptote, I need to think of what value makes my denominator 0, which would be -2. So I'm going to draw in my axes. And then I will draw in my asymptotes. So I have y equals 3. Oops. 1, 2, 3. And then my vertical asymptote is x equals -2. So notice how these shifts have occurred. Okay, now I'm not at 0, 0 anymore. I'm shifted up 3 and over to the left 2. Okay, that's because of those transformation properties. Okay, so now I have an x-intercept and a y-intercept, so I can put those on my graph. My y-intercept is 2.5, so really close to my line. And then my x-intercept is -5/3, so really close to my asymptote, but not quite touching it. So now when I make some test points, now when I'm picking my test points to see where the little swoops go, I can already see here by my intercepts that this graph is probably going to be down here in the 4th quadrant. Okay, but my asymptote was at -2, so if I substituted in a -1, I'd get a +2 over 1. Okay, so that would be up here. My 0 value is going to be the 5/2. I could substitute in 1 if I wanted to. That would give me 8 over 3, which is still in that region, still in the 4th quadrant. So I have enough information now to know that my graph would go like that. It's going to get close to those asymptotes but never touch it. And then I need to pick some values to the left of my vertical asymptote. So I would pick -3, -4, maybe -5. When I put a -3 in here, I get -9. So that's a -4 when I add the 5 over a -1. So that's going to be up here in this region because I get a positive value out. If I wanted to test one more, I could do -5 or -4, sorry. If I put -4 in there, that'd be -12 plus 5. That's going to be a negative number. And then I get a negative number in the denominator. Negative to negative divided by negative, that's a positive. So I know I would be up here. So again, I'm going to be in this 2nd quadrant where the positive values are. Okay, and before I walk away, I want to write down what my domain and my range are. So my domain is all the x values except for x equals -2. And my range is going to be all of the y values except for y equals 3. And again, there's a connection there between your vertical and your horizontal asymptotes for your domain and your range. Okay, so the best way to approach these graphs for now is just to find your horizontal and vertical asymptotes and then do a couple test points on either side of your vertical asymptote and see if you get positive values out or negative values out, so you know if you're above or if you're below your horizontal asymptote. Now if your horizontal asymptote is shifted up or down from 0, you have to make sure you're above the horizontal asymptote in the positives, or if you're, because you could still have a positive value and be below the asymptote. Okay, so don't assume that just because it's positive it's above the asymptote. It has to be a value that's positive and greater than whatever that horizontal asymptote is. So definitely make sure that you're graphing these. Look for those 6 characteristics that I was writing down of your intercepts and your asymptotes and your domain and your range. And if you have any questions, come on in and see me before school.